This is going to be an interesting talk, I think, if you heard a little bit about what free-threaded is all about. I tend not to trust other people's explanations, and I want to see things for myself all the time. So if you're that kind of people, like, you're very welcome here. So who's heard about these free-threaded stuff? Like, have you ever heard of NoGIL, GIL? Like, raise your hand if you are familiar with it. Okay. For those of you who didn't raise their hand, maybe you're punching a little bit up, but let's try to make it as approachable as possible. So who among you think that NoGIL is going to make Python faster here? Can you raise your hand? Okay. Yeah, I think you've been lied about it. Maybe not lied, but at least misled. So we're going to see a little bit of that. So let's first set the stage for what we're going to do today. So this GIL, this global interpreter log, has been abbreviated to the performance of Python programmers. Even though you could run multi-thread in Python, you can only run one thread of Python at a time. And though we've had mechanisms for concurrency in the language, the GIL has exerted a powerful influence. So it means that everything's been going around the GIL somewhat unsuccessfully, in my opinion, or at least until now. Because in 2021, Sam Gross from Meta introduced a proof of concept for a no-GIL Python. It's been the fourth time that we tried to remove the GIL since 1996. And yeah, this will mean that without the GIL, the thread will run Python on its own CPU. So we're going to have multiple CPUs running multiple independent Pythons at the same time, making the program faster, at least in theory. So we'll see about that. So another thing that I want to talk about is the CPU versus I/O bound. And I'm not going to use academic definitions. I'm going to go with my definitions. In this case, tasks whose bottleneck is running the code, like actually running the code, are called CPU bound. And the tasks whose bottleneck is waiting for the thing to do their thing and come back are called I/O bound. Okay, they're not really academic, but at least we're going to go with that. In CPU-bound tasks, the GIL is meant to stop a thread midway sometimes and move to the next thread forcibly. This is called preemptive multitasking, where in I/O-bound tasks, threads are meant to stop voluntarily while they're waiting for the I/O to complete. And to see what is this interplay between one or the other, we're going to build a load balancer. Well, a load balancer is just a server that is meant to be the entry point for most servers that are sitting in the background. It's meant to balance the load that we get from too many requests and allocate them to the different servers more appropriately, making web services mostly more scalable. The good thing about load balancer is that they combine both types of tasks. On the one hand, you have proxying the connection, which is the CPU-bound task, and the other one is the waiting for the server response to be proxied to the client, which is an I/O-bound task. The good thing about this is that maybe you're not building load balancer on your day-to-day work, but many software systems are designed this way, such as, for example, data processing, such as Spark and Hadoop, AI pipelines, and maybe scientific simulation as well, and all the stuff that we as Python developers have never had the opportunity to work on, such as video games, databases, editing videos, that kind of stuff. So if Python in the future wants to try these new exotic use cases, we're going to have some way to remove the GIL out of the way. And we're going to see how easy or how hard it is with this no-GIL or free-threaded Python. So what we're going to do today is this. First, I'm going to create a threaded GIL Fibonacci server, one in which I can send an integer, and I'm going to get the calculation of the Fibonacci for that series. The second is I'm going to stress that one. We're going to see the GIL. We're going to see what the GIL is doing, and we're going to remove it and see what is the effect of doing that. Then we're going to build a no-GIL load balancer. Like I said, it's just a server. And we're going to stress test it, and we're going to see what happens, okay? Don't trust my opinion. You're going to see what is going to happen. And I'm going to try to give a good explanation as to why it's going on, what is going on. And then we're going to switch to a more sophisticated load balancer algorithm called least connection. If you're familiar with the load balancing, this might ring a bell. And finally, I'm going to try to do a little bit of magic. So, is people ready here? Okay. So if you're trying this at home, early when I was doing this in Python US, I was using the beta version number 1. Today I'm going to use the beta version number 4, which was released 10 days ago. And this is meant to say that this is not meant to production anyway. So yeah, like I said, just try it with any version you want. Just bear in mind that you can use the 3.13 as well, which is the earliest version that we have in which the free thread is available. And all the code is available as this at the URL. I'm going to share it in Discord if you don't have to write it down if you don't want to. So I'm going to try to walk you through the code, and let's see what's going on here, okay? So this is the code that is meant to run the server. This is very basic. Your ChatGPT LLM stuff will produce it for you. It's just a server that is meant to use a TCP IP connection, and it's going to open it using the port that you selected, and it's going to run, to accept multiple connections, it's going to run an infinite loop in which it accepts a connection. It's going to create a socket, and we're going to be able to handle that connection, that socket connection, the way we want. Okay, the problem with this approach is that this code is synchronous, okay? Even though we can accept multiple connections with an infinite loop, the problem that we're going to have is that because handle is a synchronous function, it's going to block midway, waiting for the other connection to send information. And that means that we're not going to be able to accept more than one. So for that reason, we're going to have to use threads in this case. And yeah, the way we use threads in this case is very simple, which is actually the very powerful feature that threads have. It's just this. I just create a thread, I pass the function as a target, I pass the arguments, and then I just start it. And that's it. That's the beauty of threads. So yeah. How are we going to stress test this function? I'm not going to benchmark, and I'm going to say about performance here. So how do we stress test this function? So what I'm going to do is a little bit trick that I found in a video that was from Dave Bisley from ages ago. And what I'm going to do is I'm going to monitor the requests that are being sent to the client per second. How do I do that? I create a new thread in which I just wait for 1 second, and I print the numbers that are stored in a list that is going to be shared, a global shared called client, so client's list that is going to contain the zeros. And how do we increment those numbers? Well, each thread each client is going to have its own thread, and each thread is going to call this Fibonacci server. You send in just a 1 to make it like really fast response, and it's going to increment that number, the place on the list that it's associated with a 1 in an infinite loop, which means that by the time the monitor waits for 1 second, the number that is stored on that index in the list is going to be the requests per seconds that are going to be like on that server, on that client, sorry. And yeah, last but not least, we're going to have these threads that are going to be daemonic, and we're going to monitor them with a monitor per second function. So that's it. Let's see what happens. Okay. Like I said, I'm going to be using this version of Python, and I'm going to run this server on port 8000. Okay. And now, on another interface, I'm going to have these tests. On port 8000, obviously, I'm going to have 3 clients running on it. You can see that the connection is established, and we're going to have around 380, 38K, 37K, so it's fine. This is what servers do, right? So they have connections, and they send responses, and that's it. What is interesting about these is that I'm going to create a new connection, and in this case, rather than just sending a 1, I'm going to be sending something that is going to take way longer to run. And you can see that something's going on here, like another connection that is slower is doing stuff with like it's messing around with the threads that are already running, and that's the GIL. Okay, the GIL is making this long connection take precedence over the other ones. And that's because the reason is that the switching is going to happen way less often when the connection is longer than when the connection is slower. So I'm going to try to explain a little bit what's going on here, okay? Like I said, 7 multiple requests is fine because the GIL is able to switch from one to the other without having to switch in between. At least it's very likely that the switch is not going to happen in between, but rather the server is serving a whole request completely before switching to a different thread. And that's why it's fast. That said, Serving a slow query impacts this performance because the switch is going to happen in the middle. And that means that while the long request is running, the other requests have to wait. And even though there's a little bit of switching in between, the number, as you can see, was way lower as a result of these slow requests. But the good news is the thread is being suspended midway. And why do I see that? Because if we try to do this with async, the result is going to be worse. And why is that? Well, the thing about coroutines is that we're going to have to explicitly tell the language to stop midway. And because we are not able to do that, because the request is there's no await in the middle of the connection, there's not going to be any way to stop them. So whenever there's a slow request happening, the other requests are going to have to wait, and they're going to stay queued, and they're not going to run. So they're going to wait, and they're going to pile up, and they're going to pile up. So async is not going to solve a problem. It's even going to make it worse. So we're not going to see a low number. We're not going to see a 0. So what happens if we remove the GIL? Let's see it, okay? So how do I remove the GIL from what's happening? Like I said, I'm using this version of Python. And the way that I remove the GIL from the way is adding a T to it. That's all about it. Let me show you what it means. When I run Python, you can see that there's something called free-threaded build. That means that we're using this special, now non-experimental build of Python, which is without the GIL. And the good thing about 3.14 is that I can do this without having to use a parenthesis, which is really cool. Let me just say the same thing. I'm just going to create the server on the port 8000, and I'm going to have the test running on the 8000, and it's going to keep being 3. Okay, like I said, I haven't changed anything. What I just did, I just removed the GIL from the way. And the first thing you will notice is that we were running in 37, 38K, and now we're running at almost 50 sometimes, which is like very good. Like it means that maybe you're not being misled at all with the idea that the NoGIL could make things faster. And just to show you that the GIL is now no longer in the way, if I do the same with the 38, the test is unchanged. So yeah, no GIL in the environment. That means that there's no way to interfere with the other threads because the other threads are running on different CPUs. There's no interfering, and that's the way as things are supposed to be. Problem, though, is that if instead of running three clients, if I do 6, you see that the number changed, okay? That means that if I'm running more threads, then the throughput that I get per thread is lower. This is called load sensitivity, and obviously it's a bad thing because it means that when I add new clients, that means that the impact on the other threads is noticeable, which is something that I don't want. Like, especially if the server is in a very high load, we're going to have timeouts, and we're going to have errors by the fact that the server is not going to be able to withstand all the load. So for that reason, I'm going to try to build a load balancer. So what is a load balancer? Let's talk a little bit about what happens when we remove the GIL, because this problem with the long-lived request disappeared. But like I said, this load sensitivity. So we're going to build a load balancer to accommodate for that. And like I said, a load balancer is just a server. So what I'm going to do is just copy-paste what we have from the server and make a few adjustments so that we can see the load balancer in action and what it means, that load balancing into a server. So the first thing that I'm going to do, obviously, is that I'm going to change the name, and I'm going to accept the server ports, which is going to be a list of integers that I'm going to add into the function that are going to represent the servers on the background that this load balancer is responsible for. And they're going to be passed and trickled down into this handle function, okay? Why is that? Well, because when I get to the handle function with the server ports that I have available, I'm going to be able to create a new socket connection to the server that I want. And the way that I choose that socket is going to be, okay, let's start with a random choice, okay? This is going to be like the easiest way to go, I guess, right? Choosing this random port from the list is going to be the one that I use to connect, and that will keep things somewhat balanced between the servers that I have, okay? The other thing that I had to do is, rather than calculate the Fibonacci function myself, what I'm going to do is proxy the data that is coming from the client into the server that I've chosen, and whatever response the server has for me is going to be proxied back into the client, as load balancers tend to do. And yeah, like I said, finally, I'm just going to change the name, and the load balancer is going to have the server ports, which is a list that is going to have to turn the strings that I get from the script into integers, and they're going to be passed into the server ports alongside, like I said, yeah, the integers are going to be generated from the strings, and the servers are going to be running in the background as daemonic threads, okay? Hopefully this is familiar. I'm not stepping into the limits of what you understand about threads, about sockets. Is everyone okay running now, for now? Okay, cool. Yeah, so let's test it, okay? Like I said, it's going to be a random round robin. It's going to live in port 8000 so that we can test it, and it's going to have servers in the background that are going to be 8001, 8002, and 8003, okay? And I'm going to run the same test that I was running before. Hopefully we're going to see improvement, right? We're not going to see this load sensitivity. We're going to see that everything is great because now I have a load balancer which is going to distribute the balance, and no server is going to be overloaded, right? The result, yeah, like I said, it has to be 3. But this is not what's happening, okay? Recall that we had one server serving 50K requests per second, and we're not even half of that. So something's happening here. And what I want to call your attention to is that the only thing that I've really changed is this random stuff. It's the only thing that I added that's different. Well, it turns out this random is in memory safe, and that's what's messing up with us, okay? It's one of the keys about these free-threaded Python that I want to call your attention to. Rather than having one big lock that controls all the language, the free-threaded build is having hidden fine-grained locks that are making this load balancer slower. My best guess, and I haven't confirmed that, I've been people coming back to me explaining why this might be the case, but my best guess is that randoms seed, the way it's generating those random numbers, it's behind this fine-grained tool. This is what people talk about when they say about adapting to the free-threaded build. It's not that memory safe is difficult. Like if you've been an experienced developer with memory safe, you should be able to do this stuff. The problem is that you don't know where the memory safe has to be placed and where the locks, the fine-grained locks, had to be in place to make this program work. And that's why adapting to the free-threaded Python is going to be very difficult, especially if the library has been around for a long time. But load balancers don't assign ports randomly. And what do I mean by that? Is that I'm going to try to create a more sophisticated load balancing algorithm that assigns ports not randomly, but depending on the load that the current server has. And this is called least connection, and hopefully it's something that you're familiar with. Is the idea that I'm going to assign the next connection to the server that is the freer, the more available, the one that has the least connection already running in the server as the connection is coming. The good thing about doing this is that it relies on a single source of truth, like the number of connection has to be a global variable that is shared by all the connections in the load server. And why is that important for threads? Well, because this is shared mutable state, which is something that threads are really, really good at. And if you try to do this with processors, it's going to be either very complex or not as performance because of the communication that has to happen between processors. Shared mutable state is something that threads are really, really good at, and they actually built for that specific use case when you do concurrency, compared to, for example, processors or sub-interpreters. So in order to do this stuff, we're going to have to add a threading.log object, which is going to make explicit what random was hiding from us. And we're going to try to, by means of doing that, what we're going to have is one way to prove that random is actually having a fine-grained lock in the background without you knowing. This lock is what's going to ensure that the shared mutable state is only accessed by one thread at a time, rather than being concurrently accessed by multiple of one, and preserving this idea that it is the source of truth at any one time. So how do I do that? Well, rather than having server ports, a list of integers being passed into the load balancer and trickle down into the handle, I'm going to pass an object that I decided to call router, and that implements two specific methods. One is the acquire port, which is literally one that yields the port that has been selected by the router to be used by the handle, and so that it can connect and do the thing that it was doing earlier. Okay? The second thing that it has to do is it has to release the port once the connection has been closed by the client. And for that reason, we have this other method, which is going to be the release of the port. That's it. That's the implementation change in this case. So what is the router about? Well, like I said, it's going to implement these two methods, but more importantly, it's going to have the shared mutable state abstracted from the whole thing. This shared mutable state is a dictionary in which the keys are going to be each one of the ports that we have decided to implement as being the responsibility of this load balancer. And the other stuff is the lock that is going to be preserving this mutual exclusion mechanism that we need to make sure that the dictionary, this shared mutable state, is protected and memory safe. Obviously, the initialization means that no connections are being assigned to each port, so I can safely say that they are 0 at the very beginning. How does the acquire port method works? It's going to select the port that is going to be available, and it's going to select the port in which the connections, the server has the least connection. And how do I do that? Well, I just do a min function in which I have the minimum of all the keys sorted by the number of connections that are associated with that key. That's it. The fact that I'm doing this inside the context manager of the lock means that only one thread is running this code, whereas the other threads are waiting for the lock to be released and so that they can acquire it. And finally, I can just return that port so that the handler function can deal with it in a safe manner. And the release is even simpler. I just get the lock, make sure that I have access to the shared mutable state all by myself, reduce the connection by 1 because it's been already released, and then I don't have to return anything because there's no information needed for that left. So let's see what's happening here, okay? Like I said, I'm going to do this load balancer least connection, and again, 8,000, 8,001, 8,002, 8,003. Same thing, like I said. And I'm going to rerun the test, and we should be able to see that the numbers stayed at 25, 24, 23K, just like we did with random. This is probably not the mathematical proof, but at least we have some way to say, hey, this random stuff is messing with us. There's a lock inside, because by the moment we remove the random from the scenery and we add the lock, we have the same behavior, okay? So take that as a experimental proof that this is what's happening. The problem is that we still have this sensitivity, this load sensitivity stuff. When I do more servers, I keep having this problem with the connections being down. And I want to recall the idea that we have CPU and I/O bounds happening here. And for that reason, what I'm going to do is recall that we were sending just once to the server as a way to test. Well, let's change that and see what happens. In the test file, what I'm going to do is, rather than sending 1, I'm going to do and send a bigger number, like, for example, 30, okay? This will mean the connection is going to be slower to serve, because the calculation of the Fibonacci number is going to take way longer to serve. No, 63, probably too much. As you can see, now we have 13, 14. This is obviously way less, but as a result of the server having to take longer and longer to serve this request. Now that we have a task that is CPU bound rather than I/O bound, what will happen? Should we have a load sensitivity? We don't. We don't. This is very interesting. And why is that? Well, when the I/O bound was happening, the gIL was very, very efficient in the switching between the two threads. And that means that removing the gIL from the scenery doesn't make any sense, okay? It's a very, very performant machine that's been built over the years. The gIL has been with Python since 1992, so it's been a long time of performance improvements over the time, which means that if you have a task that is I/O bound, maybe it's a good idea to keep with a gIL rather than switching to NoGIL and have less performance stuff going on. But if you have something that is CPU bound, such as in this case, you're going to see that the NoGIL scales better. Like having more threads into the mix means that you can have parallelized tasks that are maybe somewhat independent, maybe not, depends on your use case. But what you're going to have is stuff that you can escalate, that is going to scale more easily. And what do I mean by that? Well, it means that depending on the number of CPUs that you have available, you're going to have the ability to push these subtasks from the project into different CPUs. And to the extent that it is the CPU, the bottleneck of your application, then NoGIL allows you to have more of them at the same time, rather than having to switch back and forth from only one. This, though, comes with a limit, and that is obviously the number of CPUs that you have on your computer. If I go harder into this, like having 10, like my CPU has only 8 CPUs available. If I go with a number that is higher, you're going to start to replicate the stuff that we were having in the gIL in the first place, and that is the thread is going to have to switch between the CPUs that are available. We're going to have some switching mechanism happening as a result of, well, I have more tasks than CPUs that I have available to serve them. So let me show you why is that interesting. Well, because if I go back to the gIL version of these, and I go with the load balancer, the same load balancer that I was using again, and I try to run these 10, the numbers go way down. And they go down in a very interesting way, which is that the numbers always add up to 13, 14, 15. So I'm just using one CPU, which is going to be available to serve as much as 15 requests per second, but it's going to, this load is going to be distributed among all the clients that I have. So rather, when I don't have 10, when I have 3, for example, we're going to have this distribution more evenly loaded in less clients. So they're going to have the ability to serve more requests per client. And finally, if I just have one thread going on, we're going to have these 15 requests per second that I was having in the first place, which means that one thread is serving this problem with one CPU. So finally, trying to summarize what I've tried to do here is that when I/O dominates, gIL is way better. But when CPU dominates, like I said, the NoGIL scales better. You have more CPUs at your disposal, and you can have the ability to remove that bottleneck out of the way, if that's your use case, which isn't always the case. Load sensitivity disappears as long as I have enough CPUs to serve. If I have more tasks that CPUs to serve, obviously I'm going to have to switch between of them. And having switched these CPUs switch from one task for another gives a gIL-like behavior, even in a no-gIL environment. So this is it. I want to give this idea that this is experimental, which means that you have to try it. gIL is faster for single-threaded. No-gIL scales better for multi-threaded programs. And this random stuff, this means that there are hidden treasures in the language that you're going to have to deal with if you want to experiment with it. Try it. Give it a try. It's fun. It's stuff that you can do. It's not that difficult. And you can see effects right away. Enjoy the rest of the conference.
Thank you, Alvaro. Unfortunately, there is no time for questions here, but you can definitely post them online or ask Alvaro directly. Thank you very much.